Hello and welcome everyone. Hello,
Good evening, sir.
good evening.
Good evening, sir.
Good evening everyone. Okay, so I was a little bit late today, but let us start immediately. So, uh, okay, anybody having any queries regarding whatever we have learned till previous session? Uh, yes. So now you can go through developing a model and analyzing and finding the results and understanding the mechanism between results and your modeling. All that you can understand, because today we are going to see initial information about lateral loading due to earthquake. Okay, hello. So I hope the things are clear to all of you. Yes, hello.
Yes,
Yes, sir.
sir.
Okay, so can we go ahead for lateral load analysis system that we are going to see? Yes.
Okay, sir.
So let me go to the proper section and I will open it with that T and then new folder. On the new folder, I may go to response spectrum and equivalent static analysis. So I'm just opening the PPT and then we'll talk about it. Okay. So this is a PPT regarding apply. Before that, let us think about uh, how the earthquake loads will be evaluated. Yes, any idea? Anything that you have in your mind, you can talk about whatever you know about earthquake. See, that may be correct, may not be correct. That we'll see. But just I want to know, do you have any idea about earthquake analysis or how the earthquake forces will be applied on any building, and then the building will be analyzed? Yes, anybody? You have the idea or you don't have any idea? हेलो. अरे बोलना तो पड़ेगा ना आपको. हाँ या ना तो बोल सकते हैं. Yes.
Sir, no idea.
Absolutely no idea.
No, just to know that the lateral forces will be converted at base as base shear,
Okay.
and that's it.
Okay. Okay. Nice. That is the see. If we do not know anything, that is nothing wrong into it. The only thing is that whether we are interested to know what we do not know. That is more important.
So actually, we have different zone, and according to that, we will
No, no. I'm not.
see.
I'm not talking about process. See the process. Many of you might know the process. Find out the zone, then find out the time period, then find out go to that calculation of seismic weight. That is a process. See, let me know how we are applying the vertical loads. So right now we have developed the frame that is subjected to vertical loads. How we applied the vertical loads? First, we have confirmed something about dead load. So that is self weight. Yes. Hello.
Yes, sir.
Yes, sir.
Then we have got enough information about floor finish. So how to calculate for floor finish and dead load, and with respect to IS 875 part 1, right? So we are going for dead self weight in terms of dead load, and whatever is that floor load or floor finish, that is again we can find out with the help of self weight and thickness and all that, right? Then in floor finish we have also included wall load. So I will say BB masonry load, or let's say wall load, and that too with the help of 875, where you are getting intensity, or self weight, and then with the help of drawing, you are calculating thickness and height and applying, and you are calculating wall load. Then you have some idea about live load, why the live loads are coming on the frame, and how to find out. That is in 875 part 2. Yes, हेलो.
Yes, son.
ये तो हमने किया ना.
Yes, son.
And all these loads are acting downward, right? And this is your frame. So you have created a frame, and then you have created you have defined these dead load, floor finish, wall load, live load, and you know that all these are under gravity load, and so their action is towards the center of earth, right? So this was a very simple example. That's why many times we do it automatically without thinking, क्योंकि हम लोग बोलते हैं ये ऐसा ही है. Now, the same way, if I apply the same type of understanding, so let's say I want to apply earthquake. Okay, so earthquake load either in X direction or in Y direction or in Z direction. Yes, right. So where from I will get the magnitude of all these loads and direction. That is the problem. If I see somehow, if I find out the magnitude, and somehow by XYZ direction, XYZ method, if I find out the direction, then is it easy for me? देख लो, मेरा कहने का मतलब है, मैंने कहीं से भी निकाला, मेरे पास कुछ जादू है, वो जादू से मुझे किसी ने मेरे कान में बता दिया कि दिस इज द अर्थक्वेक इन एक्स डायरेक्शन, अर्थक्वेक इन वाई डायरेक्शन, अर्थक्वेक इन जेड डायरेक्शन. तो कैन आई अप्लाई इट? यस और नो? डिफिकल्ट है क्या क्वेश्चन? यस, एनीबडी? सी, I'm not saying that whether that is correct or not. Nobody knows. But I have some procedure that procedure is explaining me how to find out earthquake in X direction, Y direction, and Z direction. And if I get that through that XYZ procedure, can I apply it?
Yes.
Yes. The answer is yes. Why you people are worried? Dekho, I'm not saying that it is correct. I have some procedure, and that procedure is giving me the direction and magnitude of these forces, and then I can apply it. See, here you have some procedure: calculation of self weight, calculation of floor finish, calculation of wall load, calculation of live load. That is a process that is defined in IS 875 part 1 and part 2, and the direction you know is gravity, and that's why you are applying it. Clear? See, basic अंडरस्टैंडिंग तो क्लियर करो. विदाउट अंडरस्टैंडिंग आप अप्लाई करेंगे और बोलेंगे नहीं ऐसा ही होता है, तो दैट विल बी जस्ट आई विल कॉल द पीपल एज मैकेनिकल क्लर्क्स. I don't want to create any mechanical clerk. I want the things to be applied with conceptual understanding. Clear?
Yes, sir.
Yeah.
Sir.
Now that XYZ procedure, right now we do not know. Let us say we'll try to think on it. So what is earthquake?
Vibration.
Vibration, right? That is. So what is vibration? Means let's say this is structure, and this structure, if it is vibrating in this direction, then it is a vibration. Okay. So it is vibrating like this. Yes or no? So the direction is either in this direction or in this direction. Right? Clear?
Yes, sir.
Yes, sir.
Yes,
So
sir.
I have to, that means I have to think about vibration theory. Clear?
Clear,
अगर
sir.
अगर वाइब्रेशन थियरी से मुझे कोई क्लू मिलता है, जो क्लू मुझे ये डायरेक्शन और ए डायरेक्शन दे देगी, तो आई कैन कैलकुलेट अर्थक्वेक इन एक्स डायरेक्शन, अर्थक्वेक इन वाई डायरेक्शन. क्लियर?
Yes, sir.
So where I have to concentrate? I have to concentrate on theory of vibration. अब आपने थियरी ऑफ वाइब्रेशन कब सीखा था? आई थिंक इन 12th स्टैंडर्ड फिजिक्स. यस. देखिए कैसे रूट्स कैसे है, सीखा था क्या नहीं? यस.
Yes, sir.
Yes, sir.
So you have to read 12th standard physics book again, so that you will understand basic theory of vibration. Clear? मैंने एक सोर्स बता दिया. ओके. अगर आपको डिटेल एनालिसिस की जरूरत है, एंड इफ यू वांट टू सी इट, you can go back and read the physics book that is describing theory of vibration or wave theory of light or wave theory of sound. Okay. Now what is vibration and what is the difference between vibration and motion? See, this is a particle. At some time t, the particle is here. At some time t1, let's say at some time t1, the particle moves from this point to this point, right? So that we call motion, right? Yes. Clear?
Yes, sir.
Yes, sir.
So that means you have to see the motion. You have to think on where you will find laws of motion. And where are the laws of motion? Applied physics. Your whatever you have learned in your graduation class at first year. So applied mechanics or engineering mechanics. So there you can find laws of motion. Okay. Right.
Yes, sir.
And what
Yes,
are the
sir.
parameters that define laws of motion? U, that is deformation, V, that is velocity, and A, that is acceleration with respect to time. So you have to think about the deformation, velocity, which is the rate of change of deformation, and acceleration, which is rate of change of velocity with respect to time. तो आपको ये 4 पैरामीटर्स का मैथमेटिकल स्टडी करना है. ये एक सोर्स मैंने बता दिया. नाउ वी विल गो टू वाइब्रेशन. व्हाट इज द वाइब्रेशन? सी व्हाट हैपेंस इन वाइब्रेशन. दिस इज अ पार्टिकल at say t equal to 0. It moves to this position at t equal to say 1. Then at t equal to 2, it does not move in the this direction, but it comes back. Then again at t equal to say 2, it is at this origin. Then again it moves in this direction at t equal to 3.
Yes, sir.
Okay. So 0, 1, 2, 3, and then again 4. So the particle is moving from one point to another, then coming back, then again moving in another direction and coming in this. So in this position, if I say this particle which is at equilibrium, okay, that is going to its maximum position, then coming back at equilibrium, then going to maximum negative position and coming back. So the time taken by this particle, which is started from t equal to 0, going to its maximum deformation, then coming back, then coming to maximum negative deformation and coming to this. So the time taken by this particle to complete one cycle. So it started from this, it started like moving like this and again came back to this. So the time taken will be considered as time period. So time period is what? Time taken to complete one cycle of a vibratory motion. Because vibratory motion does not go anywhere. It just goes to maximum deformation to the right, come back to original, come back, goes to maximum deformation in the left direction and coming to this. Now if I draw the graph of this particle, let's see this is one point. The particle is over here and it is moving at this focus in a circular motion. So is it one cycle? Okay,
Yes, sir.
so I will say that position vector of the particle is like this with this some theta. Okay, so it will start moving in this direction, coming back to this and coming this. Now, so one cycle has completed. Then again it starts another cycle. Again it is moving in this. So how much time it will take to complete second cycle? If it is taking 3 seconds to complete one cycle, then in second cycle, how much time it will take?
3 seconds.
3. And say at fifth cycle,
3 seconds.
3. So when the time taken to complete one cycle for one particle to complete one cycle is remaining same or it is constant, cycle after cycle, cycle after cycle, cycle after cycle, then it is called a free vibratory motion with no damping. So I will say that damping is equal to 0 because it is moving in a circular path, right? Clear हुआ? So
Yes, sir.
free vibration. Now let us say that this is a particle and it is not moving in circular, it is moving in elliptical manner like this. Let's say this is the position. तो यहां से शुरू हुआ और यहां पर आया, तो एंगल तो सेम है. सो दिस इज फर्स्ट साइकिल. सेकंड साइकिल में क्या हुआ? यहां से शुरू हुआ, यहां पे आया, तो दिस इज सेकंड साइकिल. सिमिलरली यहां से शुरू हुआ, यहां आया, थर्ड साइकिल. Let's say the first cycle, it is taking time equal to say 5 seconds. In second cycle, it will take a time less than 5. Yes or no? It will see the traversing is lesser distance. So it will take, let's say 4. Then in third cycle, it might take 3. In fourth cycle, it might complete 1. And finally, it will be at equilibrium. Now here it is not moving, so it is rotating, but it is not going anywhere. Clear? So this process of decreasing the time or amplitude, let's say amplitude, that is considered as a damped vibration. That means damping is somewhere. So that is a damping. Clear?
Yes, sir.
Yes, sir.
So undamped vibration, you will see a sequence something like this. So every time from x-axis equal to 0 to this. So this is your one cycle. Okay. And you can see this is your second cycle. And you will see that time taken is same, T1, T1. So this is undamped. Okay. There is no damping, and that's why it is constantly taking the same time interval to complete one cycle. Right? Let's say this is let's say this is the time in seconds, and the motion is coming something like this. So the first cycle will end over here. Second cycle will end over here. Third cycle will end over here. So what you observe? T1 is greater than T2. T2 is greater than T3. And T3 is greater than T4. Yes.
Yes, sir.
So this thing happens because of frictional losses in that vibratory motion, and those frictional losses or any other losses, because of that you see amplitude getting reduced. Now the same thing I will just explain in this. Let's say this is some ceiling, and this is a string of wire, and there is a ball over here. Okay. Now somebody pulls this ball and brings it over here, and then he pushes. That's all. Then the bar, it will come like this. Pendulum ऐसा ही होगा ना?
Yes,
Yes,
sir.
sir.
Yes, sir.
Then you will see that second time the pendulum will not reach to this, but it will reach over here. Then it will come over here. Then finally it will come over here. Then over here. And finally, after some time, maybe 3 seconds, 5 seconds, depends on how much force that you have applied, how much distance, how much angle that you have stretched, and what is the mass of this pendulum. So, but you will see that these vibrations finally will come to an end, and finally you will see that again your pendulum will have a equilibrium like this. Right? Clear?
Clear, sir.
That means the amplitude of vibration is constantly getting reduced, and that reduction in amplitude is because of the external frictional energy losses that were applied. ये इतना समझा?
Yes, sir.
Yes, sir.
Yes, sir.
Now we will go and see. Let's say this is your earth. Okay, this is the surface of earth, and somewhere you have a building that you have constructed is something like this. Okay, inside the earth some activity happens, and I'm not right now interested as a structure engineer, but as a geophysicist you may be interesting, find out why earthquake produces. But as a structure engineer or civil engineer, I'm not interested why the earthquake has erupted, why the activity has a cause, but I want to concentrate only on this building, that what will happen if somewhere inside the earth earthquake erupts and there will be the vibrations. Yes, all these vibrations will come to this and they will hit the surface, and the surface will be vibrated to and fro. Clear?
Yes, sir.
So there will be acceleration, and this acceleration is called acceleration due to gravity due to this earthquake. Right? Now, as the accelerated over here, the base of the building will move like this. But the building has a mass, or I will say the building has weight, and weight divided by g will be a mass. Clear?
Yes, sir.
You may have the weight of the building, say 1000 kilonewton. So if I divide that by gravity, I will get mass. Okay. Now this acceleration creates a motion at the base, and that's why base will vibrate with this acceleration, but this mass has a tendency to oppose the acceleration, and that's why we say that laws of motion, Newton has given you a formula that F equal to m times a, right? Or let's say ag. Clear हो रहा है?
Yes, sir.
Yes, sir.
कनेक्शन देखो, कनेक्शन ढूंढो, बिकॉज वी वांट टू फाइंड आउट फोर्सेस दैट आर क्रिएटेड ड्यू टू द अर्थक्वेक. अर्थक्वेक एक्चुअली कोई फोर्स साथ में नहीं लेके आता है. अर्थक्वेक इज अ वाइब्रेटरी मोशन and it will vibrate base of the earth, or base of the not earth, base of your foundation or building. Create. Clear हो रहा है?
Yes,
Sir.
sir.
Now can I find this? I can find it with the help of earthquake analysis, and that is seismograph. And you may see that most of the time you might have seen a seismograph, something like this. Yes. And finally this. So this is your T, and this is your acceleration. Acceleration due to earthquake. And it is so rapid. It is not something that like this. So it is not a constant amplitude, so it is changing so rapidly. So the if you find out a seismograph, you will see the seismograph of any earthquake will give you content in so acceleration in x direction, acceleration in y direction, and acceleration in upward. In our case, as we are applying the units of or system concept of ETAG, that vertical axis is z. So I will say that any acceleration will have three components: one in x direction, one in y direction, and third in z direction. Clear?
Yes, sir.
Now, if I find this and if I can analyze this, see, I don't know how I am going to analyze, but right now I am saying that if I have enough knowledge about earthquake, seismograph, and if I can find out at every time t equal to something, if I find out AG and I put it over here, M I have found out with the help. Can I find F?
Yes, sir.
So
Yes,
that is
son.
the process. That is the process. Clear?
Yes, sir.
So
Clear, son.
yeah. So you have to get the data of earthquake. You have to get the data of your entire structure divided by G. So you will get M, and if you apply that, you will get F. Simple. या अभी भी कुछ डाउट है?
No, sir.
ओके अब जितना मैं सिंपल बोल रहा हूँ उतना सिंपल है नहीं, क्योंकि उसमें बहुत सारा इंजीनियरिंग एनालिसिस है, देन लॉट ऑफ अदर थिंग्स है. बेसिकली अर्थक्वेक इज अ वेरी कॉम्प्लिकेटेड फिनोमेना, एंड every earthquake is different. So you cannot say that 10 साल पहले ये earthquake आया था, उसका एनालिसिस करके I can apply it in future, because every earthquake is very complex phenomena, and every earthquake has a frequency content. So let's say frequency content. Then it has what do you mean by frequency content? It has every time or fraction of time it varies its frequency. Let's say omega 1 is frequency at t equal to 1. Then immediately fraction of second it is converted in omega 2. Fraction of second it is converted at omega 3. So how many number of frequencies? N number of frequencies. So earthquake is not coming with one frequency. It is coming with n number of frequencies. Clear? Now you will ask me, what do you mean by frequency? Clear? Hello.
Yes, son.
Now frequency is very simple, as you have seen that concept of this single pendulum. Okay, let's say pendulum is going up to this, then it is going up to this. So this is the so let's say it is going to this, then coming back, then going on reverse direction and coming back. So the time taken to complete one cycle is called period. Okay, and it is a you can say that it is a circular motion, because it starts from this and comes to this. Okay, so now for this, if I say it has some perimeter or diameter, let's say it has some diameter. So how much will be the perimeter?
2 pi r.
2 pi r. Okay, so r is this distance. Okay, or you can say okay, let's say call 2 pi r. Okay, then this is the total distance that is to be covered, and let us say it is rotating with some omega value. So omega. Okay, it is rotating with omega. So that is omega is radian per second. So in 1 second, it is moving with omega 1 radians. Clear? Hello.
Yes, sir.
Yes, son.
So this is the omega 1 is the frequency, I will say that. And now you will find out the equation as 2 pi upon omega. So that is the time period. That is that is that is the total time period that is required. So 2 pi upon omega, where omega is in radians. Now, if this circular frequency, if I convert, let's say this is circular frequency, and if I find a projection on x-axis, so what will happen at t equal to 0, it will be over here. At t equal to 1, it will be over here. At t equal to some, it will be here. So I'm finding the projections. And if I find the position on x-axis, I will get moment like this. Because the point is moving from this point to this point, then coming back, then going this and coming back. The projected point, actually the circular motion is converted on x and y. So let's say this is your deformation. So whatever may be the deformation, and this is your t. You will find this cycle. And that's why we say this is one cycle. Then there will be another cycle. Then there will be third cycle. And on circular path, you will find it moving like this. Okay. So this time period is equal to 2 pi upon omega. That you can check. Yes?
So 2 pi r upon omega or only 2 pi upon omega?
No. 2 pi upon omega. See, you just check S equal to ut. See, this is your formula in linear motion. आपको थोड़ा वो डायनेमिक्स है ना, जो आपने अप्लाइड मैकेनिक्स में या इंजीनियरिंग मैकेनिक्स में डायनेमिक्स करके एक पार्ट था, स्टैटिक एंड डायनेमिक्स, याद आ रहा है?
Yes, sir.
Yes, sir. Yes, sir.
तो उस समय हमने वो ऑप्शन रखा था और स्टैटिक पे स्टडी करके हमने वो सब्जेक्ट क्लियर किया. So see, always see that distance is equal to what I will say, S equal to u of t, or v equal to velocity is equal to u upon t. So this is velocity, this is deformation, and this is time. So you can say deformation equal to v upon t. So if you apply this in your circular diagram, you will find this basic formula, which is t equal to 2 pi upon omega. That you can go and see applied mechanics book. You will find it. So actually, right now I don't want to move into that. I just want to say that if this is the t equal to time period is equal to 2 pi upon omega. That is where omega is radial or circular frequency. And if you want to find out frequency in hertz, then it will be 1 upon t.
T.
That means frequency, if you convert this, it will be omega upon 2 pi. Clear? Hello?
Clear, sir. Clear.
Yeah. So you are interested, or I will say that you must concentrate on these formulas, where here we say that t is time period and f is frequency in hertz and omega is frequency in radian per second or circular frequency. Okay. Now every earthquake is having bunch of frequencies, whether you call it hertz or whether you call it as circular, it is one and same, because you know f, you can find out omega. If you know omega, you can find out f. So it is interrelated. It is not independent. Okay. So the earthquake that is generated somewhere here, it generates waves of energy, and these waves come to a surface where you are having a structure, and this structure, base of this is vibrated with n number of frequencies, and that's why this will exhibit vibration just like a pendulum. It will also vibrate. I will call this, let's say, consider it as a mass. Entire mass is concentrated over here, and this base is vibrated. Then you will see the result that it is vibrating in like this. Okay. Yes.
Yes, sir.
And this is mass, and the building will have some stiffness. Let's say entire building is having a stiffness. Let's say I will call it over here K. Then you you can find out omega square, which is nothing but stiffness divided by omega, or you can say omega equal to root K by omega. Okay. No, K by M. K by M. Omega square equal to K by M. That is a standard formula that you can find out in any structural books. But I will just mention here omega, which is a property of the structure, is a function of stiffness and mass. Clear?
Yes, sir.
So earthquake will come with n number of omega. Okay. So earthquake will come with bunch of frequencies, and this structure will also have bunch of omegas, because entire mass, I am saying here entire mass is concentrated over here, but actually you can see that the mass is concentrated at this, mass will be concentrated at this, mass will be concentrated at this, and mass will be concentrated at this, and this will have a K1 as stiffness, K2 as stiffness, K3 as stiffness, K4 as stiffness. So the building itself will have its own pre-vibratory motion shapes, which will define with the help of K and M. So if you know the stiffness of ground floor, you know the mass at this story, you will find uh, a frequency for this as omega equal to K upon M. Similarly, this stiffness will be different, this mass will be different. That means this will also be. That means n number of masses will provide you n number of frequencies. Clear?
Yes.
So now I will say that, and this is very important concept. Uh, when the building will vibrate maximum, or when the building will be subjected to maximum deformation. Kab? See, I don't want engineering answer. I want a common sense answer. Let's say I'm having a building, mathematical solution. Let's say I'm having a single story building, and that's why this is a stiffness that I'm considering, and this is the mass I'm considering. So it is having M, and this is K. So I will have only one omega, which is equal to square root K upon M. How to calculate M and K, that is again a different concept. But let's say that I have calculated the entire stiffness of the ground floor, and I have calculated entire mass of the floor, and that has been effectively assumed concentrated at floor level. So this will be the height. Clear? Hello.
Yes, sir.
Now I want to know from you that when this mass will deform to its maximum position, maximum, either in positive direction or in negative direction. देखो ये अगर आप सोचेंगे नहीं ना तो
When the
आप
intensity of vibration is very high, or in
When
resonance.
H is more.
When
Yeah.
mass is less.
Yes, mass is less, height is more. You're on exactly, you're saying conceptually you are saying correct, but I will say that uh, when the building will offer less resistance. अब देखो ऐसे मैंने इसको मूव किया तो ज्यादा कब मूव होगा जब ये ऑफर नहीं करेगा रेजिस्टेंस और लीस्ट रेजिस्टेंस. क्लियर. बहुत कम रेजिस्टेंस ऑफर करेगा तो वो ज्यादा मूव होगा ना.
Yes.
So
Stiffness will be less, then it will offer least resistance.
या दैट इज ओके. मैं वहीं पर आने वाला था क्योंकि अगर रेजिस्टेंस कम है तो डिफॉर्मेशन ज्यादा होगा. राइट. एंड रेजिस्टेंस कब कम होगा जब स्टिफनेस लीस्ट है. मान लो अगर मुझे इसको कंट्रोल करना है वाइब्रेशन तो मुझे क्या करना पड़ेगा कि बढ़ाना पड़ेगा. दैट इज द स्टिफनेस.
Yes, sir.
और अगर आई वांट टू इंक्रीज द डिफॉर्मेशन तो क्या करना पड़ेगा कि घटाना पड़ेगा. वो आपको यहां पर ही पता चलेगा कि घटाया तो फ्रीक्वेंसी घट जाती है, मास घटाया तो आई मीन कि अगर इंक्रीज किया तो फ्रीक्वेंसी इंक्रीज होती है, मास इंक्रीज किया तो फ्रीक्वेंसी डिक्रीज होती है. इतना तो पता चला आपको. अब one more property is that the building will offer least resistance when it is allowed to vibrate in its natural mode. मतलब उसका जो ये बिल्डिंग है, ये बिल्डिंग को अगर मैंने वाइब्रेट किया with this is a natural frequency of the structure because it is a property of the structure. K क्या है स्ट्रक्चर का प्रॉपर्टी, m क्या है स्ट्रक्चर का प्रॉपर्टी, एंड ओमेगा डिपेंड्स ऑन k by m. So ratio of k and m. So omega is a natural vibration frequency of the building and the building will vibrate to its maximum position when it is allowed to vibrate in this frequency. बात समझ में आई?
Yes, sir.
Yes, sir.
Now this earthquake is coming with bunch of frequency and every fraction of second it is changing in frequency. तो कभी तो होगा ना ये frequency इस frequency को match होगी. There will be a time, no?
Yes, sir.
Yes, sir.
That time the building will vibrate maximum, and that is why,
Resonance.
yeah, that is a resonance condition. But resonance के लिए और एक condition जरूरत होती है कि that frequency should remain for larger time.
Yes, sir.
But fortunately, earthquake does not vibrate with any one frequency for a longer time. At every fraction of second, it changes from W1 to W2, W2 to W3, W3 to again W1, again W2, again W3, again W2, again W1. वो change होते रहता है. Right, this. And that's why resonance, और अगर अगर ये अर्थक्वेक एक ही फ्रीक्वेंसी से वाइब्रेट होगा ना, तो ये फ्रीक्वेंसी जिस बिल्डिंग के फ्रीक्वेंसी को मैच होगी ना, वो बिल्डिंग सीधे कोलैप्स हो जाएगी.
Collapse.
That's why I say, fortunately for us, though the earthquake is coming with n number of frequencies, it does not vibrate with any frequency for longer time. Within fraction of second, it changes its frequency, and that's why we can analyze the building, we can design the building. नहीं तो दुनिया में कोई ऐसा आदमी नहीं होता था वो अर्थक्वेक प्रूफ बिल्डिंग और अर्थक्वेक रेजिस्टेंट बिल्डिंग बना सके. कोई ना कोई बिल्डिंग जो ये अर्थक्वेक के फ्रीक्वेंसी को मैच करेगी वो तुरंत गिर जाएगी, क्योंकि रेजोनेंस हो जाएगा. रेजोनेंस में पता है ना आपको, ये ऐसे चलता है और सडनली ऐसे होता है.
Yes, sir.
सडनली ऐसे होता है. तो इतने हाई एम्पलीट्यूड को नोबडी कैन सस्टेन. बहुत सारी चीजें, बट जो बेसिक चीजें है वो मैंने बताई. तो हम लोग फोर्स कहां से निकालेंगे? विद द हेल्प ऑफ m into a, right? So we may say ax, ay, az, so that based on that you will find it fx equal to m into ax. So m will be the mass of the building and ax will be some acceleration that we are going to calculate with some external with the help of seismograph. Clear? Then that force you will see that finally I will get the force of this building. So if earthquake is coming like this and it is providing acceleration in this, the base shear, that is VB. So this will give me base shear. Now this base shear will be distributed at every floor like this. What is the distribution law? ये कैसे? You may say, sir, how many five story? Let's say this is 100. So I can say that I will apply 50, 50, 50 at every floor, so that the building, and then I will design the building. Another will say that I will assume this law. Third one may say I will assume this law. So accordingly, but you can distribute base shear at every floor level. तो वही हम इक्विवेलेंट स्टैटिक लोड मेथड में करने वाले हैं. क्लियर? तो हम लोग क्या करेंगे? वीबी निकालेंगे और एवरी फ्लोर को डिस्ट्रीब्यूट करेंगे. और वीबी कैसे निकालेंगे? विद द हेल्प ऑफ दिस. आई थिंक क्लियर हुआ होगा बहुत सारा.
Yes, sir.
तो आगे चले.
Okay, sir.
Okay. Now we'll come to the practical problem. So let's say we are considering this problem. So we are having a problem statement as we are having a number of bays in x direction with 4 bays with 5 meter each bay, and in y direction we are having 3 bays of 5 meter. So it will be 15 by 20 building, and we are saying that this building is this shape. So regular shape building, at every cross section we are having columns. Okay, so this is the plan of the building, and this is the elevation of the building, where ground story height is 4.2 and every upper floor is having a height of 3.2. Clear? So this is the data. समझ में आया?
Yes, sir.
Yes, sir.
Yes, sir.
Now we are going for input data, that is location of this building is Bhuj. Soil condition at this building, where the building is standing on earth, is soil. Foundation soil is medium steep and frame is RCC. Clear? Now we are assuming that Okay, let me show you if this is a plan. Okay, so the mass is distributed all over the entire area. Now I am saying that I will find out center of mass like this, and whatever may be mass of this floor, I will assume it to be concentrated over here. So that is my mathematical assumption for some calculation. See, every time when you are going for analysis, you have to make assumptions. अगर आप assumption नहीं करेंगे, तो you cannot deal with any physical problem. Clear? So एक assumption मैंने क्या किया? Every floor is assumed to have a mass concentrated at one point. Clear?
Yes, sir.
Now that lumped weight due to dead load, I'm saying that at floors it is 12 kilonewton per square meter. Dead load on roof is 10 kilonewton per square meter. Live load on floor is 4 kilonewton per square meter, and live load on roof is 1.5 kilonewton per square meter. Right? Yes?
Yes, sir.
So I will say that if I'm having this floor, so it is 20 and this is 15. And if I want to find out dead load, total dead load, let's say this much. How much it will be? Area is 50, 15 multiplied by 20. And per square meter, how much I am considering? 12. So total low weight mila ki nahi? So this is kilonewton per square meter, this is meter, so I get total weight. And then I am assuming it to be acting over here. So instead of considering entire floor, I am considering only one point, and I will apply this much. How much it is? Whatever it is. Clear? Hello.
Yes, sir. Clear.
So that is what I want to explain it over here. Okay. Now, so due to dead load, I am considering 12 kilonewton per square meter on floor, 10 kilonewton per square meter on roof. Live load, I am considering 4 on floors, and live load on roof, I am considering 1.5. So this is again, that's why I say that it is input data. Okay. Now, what is the aim? My objective is to find out story shear and find out base shear by equivalent static method. Okay, क्लियर हो रहा है?
Yes, sir.
ये दो चीजें मुझे निकालना है. अब I don't know what is story shear, but what here I will find out by equivalent static method. Now, why I am calling it equivalent static method? Let us explain. Let us see into it. See, actually, you say that F equal to M into A. And this A is varying with respect to time. So at t equal to something, A will be different. At t equal to 2, A will be different. That means this F is not constant. Though M is constant, A is variable. That's why F will also be variable. Right? Yes?
Yes, sir.
It is not static. It is dynamic. Anything which changes its magnitude or direction at different time, that is called a dynamic. So actually, this force is not dynamic. I mean, not static, but I am converting it in equivalent static. Actually, I should go for dynamic analysis. Whenever, whenever you are coming with acceleration or velocity or deformation with respect to t, that is at t equal to something, it will change. That means it is not constant over the time. Clear हो रहा है?
Yes, sir.
Yes,
So
sir.
actually, I must go for dynamic analysis, but dynamic analysis is complicated and I'm not interested. So what I will do, I will convert entire dynamic load in static load, and that's why I'm calling it as equivalent static. And that's why the method that is using equivalent static load is called equivalent static method. So in fact, you are converting your dynamic problem in equivalent static problem. Clear?
Yes, sir.
Now you can go and look into this. So this is what happens. I have already explained. Actually, the base is vibrating, but you can consider base as a fix and entire vibrating in an opposite direction. So if acceleration is applied, now this is acceleration due to earthquake. It is applied in positive x direction. Actually, you see the movement in negative x direction. Clear? Hello.
Yes, sir.
Okay. Now let's see. Now here starts your equivalent static load method. Now, if you go to 1893 under clause 7.5.3, design seismic base shear. This is the definition of design seismic base shear. It says that it is nothing but total design lateral force or design seismic base shear, which is acting at base along any principal direction. What principal direction means? It will be in x direction, it will be in y direction, or it may be in z direction. That is, these are the three principal directions. So along any principal direction shall be determined by the following expression. So it says that if you want to find out VB, see, I'm talking about this code, this clause of 1893. It says that you can calculate VB by this formula. Now, what is W? You can see seismic weight of the building. Okay, we'll see that actually we found out only the total weight, but what is the difference between weight and seismic weight? That we'll look into the further. But let us assume that W is seismic weight of the building. So by any means, if you calculate seismic weight of the building, then you have to multiply by AH. And what is this AH? AH is design horizontal acceleration spectrum value as per 6.4.2 of the clause using fundamental natural period T as per clause number 7.6 in the considered direction of vibration. That means if you are considering direction of vibration in x, you have to find out tx. If you want to find out uh, vibration in y direction, then you have to find out ty. Okay. Now that ty will be found out with some another expression, but let's say what is the I'm just here explaining what is the meaning of ah. Now let me know what could be the unit of ah. If you see this, so VB is in kilonewton. This weight is also a force that is in kilonewton. So what will be the unit of AH? क्या होगा AH इक्वल टू kilonewton divided by kilonewton. ये क्या है? इट्स अ रेशियो. समझ में आ रहा है ना? हेलो.
Yes, sir.
Yes, sir.
So it does not have any unit because it is a ratio, and that's why it is called a seismic. It is a design horizontal acceleration. AH is actually it's a coefficient that is calculated with help of this and this. That we'll see later on. So AH is a coefficient. Once AH will be in X direction, once AH will be in Y direction. And then you will find out base shear in X direction and base shear in Y direction. Clear? So there is no magic in this formula, that you just have to find out two quantities. One is seismic weight and another is horizontal acceleration, design horizontal acceleration spectrum value. देखते हैं वो क्या है. Where is, okay, you can see here design horizontal seismic coefficient, because it is a ratio. Now this design, see 6.4.2, आपने यहाँ देखा, what he is saying, you calculate it with the help of clause 6.4.2, and now if you go to the clause 6.4.2, it says that design horizontal seismic coefficient AH for a structure shall be determined by following expression. ये थोड़ा आपको इनिशियली बहुत डिफिकल्ट लगेगा, मगर ऐसा कुछ नहीं है. वो बोलते हैं ना, मान लो कि आप किसी नए शहर में गए हो और आपने किसी को पूछा, भाई साहब ये एड्रेस कहाँ है, वो बोलता है आगे जाके वो सामने वो आदमी है उसको पूछो. तो आप उसके पास जाते हो, वो बोलता है नहीं नहीं आगे जाके और किसी को पूछो, फिर आज फाइनली आप जाते हैं. तो ये ऐसे ही है. पहले तो ये बोलता है वी भी कैसे निकालना है, इट इज ए एच इंटू डब्ल्यू. अब आप बोलते हैं भैया ए एच कैसे निकालना है, तो वो बोलता है जेड बाई टू आई बाई आर एस ए बाई जी. अब जेड क्या है, आई का है, आर क्या है, एस ए बाई जी क्या है, वो आगे जाके देखना पड़ेगा. सो अगेन the thing is very simple, the theme is very simple. You have to find out AH, and if you want to find out AH, you have to find out Z, I, R, SA by G. Okay, 2 you know it is a constant, so don't ask me how to find out 2. Yes, clear हो रहा है?
Clear है sir.
हाँ, तो हमारा अभी एम क्या है, हमें जेड का पता लगाना है, आई का पता लगाना है, आर का पता लगाना है, और ये एस ए बाई जी का पता लगाना है. ठीक है, देखते हैं. अब देखो जेड क्या है, जोन को फैक्टर कहां पे दिया है, टेबल नंबर 2, और वो क्या है, फॉर मैक्सिमम कंसिडर्ड आर स्क्वायर. देन सर्विस लाइफ ऑफ द, आप पहले इतना ही बोल दो कि जेड इज द जोन फैक्टर. नाउ इंडिया has been divided. अगर आप मैप ऑफ इंडिया देख लेते हो तो you will see that India has been divided in 4 zones. Zone number 2, zone number 3,
4 and 5.
4 and 5. So where is zone number 1? It is merged in zone number 2. Okay. Now this zone is having a Z value equal to 0.1. This zone is having a zone value of 0.60. This zone is having a zone value of 0.20.
0.24. Yes.
And this zone is having a value of 0.30.
0.36.
Now, if you want to know कहाँ से लाया, क्यों लाया, इसका क्या है, तो you will have to work on all these zone, how to find out zone factor, what is maximum considered earthquake, what is design basis earthquake, वो डिटेल है. अगर आप कहेंगे कि भैया ये 1893 ने दिया है तो डेफिनेटली आई कैन बिलीव इट. दैट मीन्स there is no problem for Z. You just have to find out the location of your structure, whether it is located in this zone, this zone, this zone, or this. So I will just explain that this is a mild zone, and as the Roman number increases, the zone factor goes on increasing. That is seismic activity. That Z is defined based on maximum considered earthquake in that area. Again, that is determined by the previous data evaluation by seismologists. Okay, so based on that, they have divided entire India in 4 zones, and this this may change afterwards because uh, uh, this will be considered with the previous record of earthquake. अगर किस नए एरिया में earthquake हो गया तो इसमें changes हो जाते हैं. So don't consider this as a final value because it might change after 10 years. If your area is subjected to earthquake, you will get the data, and based on that data, there will be a little bit changes. So to your location might to change from 2 to 3, or if it is 3, 3 to 4, or if it is 4, 4 to 5. So that depends on how much data that you are having. Clear? Yes.
Yes, sir.
तो
Yes, sir.
तो ये जोन को अब डरने की जरूरत नहीं. डरावना लग रहा था, इतना डरावना नहीं है. बस आपको 4 वैल्यू में से एक वैल्यू लेना है बेस्ड ऑन द लोकेशन ऑफ योर स्ट्रक्चर. नाउ दिस I is what? Importance factor depending upon the functional use of the structure, characterized by hazardous consequences and its failure, post-earthquake functional needs, historical value, etc., etc., economic importance. मैं इतना ही कहूंगा कि रेसिडेंशियल बिल्डिंग के लिए यू कैन गो फॉर I equal to 1, और से if रेसिडेंशियल बिल्डिंग है या कमर्शियल बिल्डिंग है but there are number of occupants are more than 200, you can go for I equal to 1.2.
1.2.
And if you say that your building has post earthquake functional needs, etc., historic value, or economic importance, then you may go for I equal to 1.5. बस 3 ही वैल्यू है. तो Z and I निकल गए. अब डर कम हो रहा कि नहीं हो रहा? यस. हेलो.
Yes, sir.
थोड़ा कम हुआ ना डर?
कम हो रहा है सर.
हाँ. अब देखो आगे जाके आप बोलेंगे बहुत आसान है, इसमें कुछ दम नहीं है. देखो, see this R. Now try to read this response reduction factor depending on perceived seismic damage performance of the structure, characterized by ductile and brittle deformations. However, the ratio I by R shall not be greater than 1. The value of R for buildings are given in table. तो पहले ही बताओ ना भैया, टेबल 7 देख लो तो हम देख लेते हैं ना, इतना डरावने की क्या जरूरत है. राइट? यस.
Right, sir.
So finally, you have to see table number 7 that has been produced by 1893. But मैं आपको ये थोड़ा समझाने की कोशिश करता हूँ सरल लैंग्वेज में. ये थोड़ा, अब देखो क्या हो रहा है, ये क्या बोल रहा है? रिस्पॉन्स रिडक्शन फैक्टर. मतलब it is a factor which is reducing the calculated response. इतना तो समझा? Yes or no?
Yes, sir.
Yes, sir.
Now, this response reduction factor is depending on perceived seismic damage performance. अब ये क्या नया चक्कर है, देखते हैं. ओके, तो पहले तो इतना पता चला कि ये रिडक्शन फैक्टर है एंड ये डिपेंड करता है perceived seismic damage performance of the structure. Also, it is characterized by ductile. So, ductile और ब्रिटाइल डिफॉर्मेशन. मतलब वो जो डैमेज हो रहा है वो डक्टाइल है क्या ब्रिटाइल है, उस पर वो डिपेंड करता है. परसीव्ड सिस्मिक डैमेज पर डिपेंड करता है, और ये रिडक्शन है. क्लियर? अब आके जाके देखते हैं कि व्हाई इट हैज बीन इंट्रोड्यूस्ड. आपने अब तक क्या किया? you have analyzed the structure for linear elastic force analysis. ऐसा ही था ना? Yes.
Yes, sir.
So now समय आ गया है. What is linear elastic behavior? अब देखो मैं सिंपल बताता हूँ. I will just try to make it simple. See, on x-axis I will draw deformation, and on y-axis I will draw force. Okay, and I will have a structure something like this. And I'm applying a force over here. So what will happen because of this force? The structure will deform. Clear है ना?
Yes, sir.
ये कैसे डिफॉर्म करेगा? शायद ऐसे डिफॉर्म करेगा. So let's say I will plot this deformation. Okay, and here is F. So I will plot deformation on x-axis and force that is required for this deformation on y-axis. Clear? Yes?
Yes, sir.
Say when delta is equal to 1, F was equal to this. When delta was increased, F was also increased. So increase. So up to certain level, it was increasing in this direction. So the graph I am getting linear. Yes? Clear हो रहा है? This is the graph. That means for this delta, this is force. For this delta, this is force. For this delta, this is force. And for this delta, this is the force. So I will call this as delta y and this as Fy. अब ये ग्राफ क्या दिखा रहा है? लीनियर वेरिएशन. हेलो.
Yes, sir.
तो द ग्राफ मुझे दिखा रहा है लीनियर वेरिएशन. So that's why I will say that it is a linear variation up to delta equal to y. Force is equal to Fy. Forget about the amount. I'm just trying to concentrate on the analysis concept. So ये delta y कुछ भी हो सकता है. Now this delta y, अगर मान लो कि ये f मैंने रिमूव किया धीरे धीरे. मैंने पहले क्या किया? I increase f linearly and I found out delta y on that. Clear? अब मैंने यहां से वो इंक्रीज किया. अब मैंने वैसे ही रिमूव करना शुरू किया. I started removing that f. Finally, I will see that I will come back in the same line. So when f will be 0, delta will also be 0. Yes?
Yes, sir.
Yes, sir.
That means there is no damage in the building. थोड़ा बहुत deformation हुआ. The moment I removed the force, the building came back to its original position. Yes or no?
Yes, sir.
Yes, sir.
And this is the maximum up to which I get the deformation in elastic manner. अगर जैसे मैं f बढ़ाता हूं, delta goes on increasing, but it will move something like this. And this will be my delta max. Let's say this is my delta max. ये लीनियर है? Beyond
No.
delta y, it is not linear. That's why it is called non-linear behavior. Non-linear. Clear हो रहा है?
Yes, sir.
Now, elastic के बाद मैंने बोला बहुत हो गया यार इसके साथ खेलना, अभी थोड़ा थोड़ा रिमूव करते हैं। तो थोड़ा थोड़ा अगर मैंने रिमूव किया, द स्ट्रक्चर विल कम बैक लाइक दिस, और यहाँ पे रुकेगा। तो दिस इज माय परमानेंट डिफॉर्मेशन। अब आई कैनॉट फाइंड, सो दिस इज माय डेल्टा परमानेंट। ये रेसिडुअल डिफॉर्मेशन रहेगा ही रहेगा। Try to imagine that you're stretching a rubber beyond its elastic limit and you are removing, then उसमें डैमेज दिखता है या नहीं दिखता? उसका ओरिजिनल शेप तो नहीं मिलता है ना?
No, sir.
डायमीटर या उसका क्रॉस सेक्शनल साइज कम होता है।
Yes, sir.
Yes, sir.
That we call as residual deformation or permanent deformation that you cannot recover. The deformation that you cannot recover after removing the force, that is called permanent deformation, and that's why it is called non-linear elastoplastic. So actually this is a plastic region and this is elastic region. तो अगर आपका डिफॉर्मेशन इन इलास्टिक रीजन में है तो बिल्डिंग विल नॉट गेट डैमेज्ड, वो थोड़ा डिफॉर्म होगा। द मोमेंट द फोर्स इज रिमूव्ड, द बिल्डिंग विल कम टू इट्स ओरिजिनल पोजीशन। बट इफ द बिल्डिंग इज डिफॉर्म beyond elastic range, then there will be some sort of residual डिफॉर्मेशन हो जाता है ना। बहुत ज्यादा क्रैक होने के बाद वो क्रैकिंग पोजीशन में ही रहेगी बिल्डिंग। क्लियर हो रहा है ना?
Clear, sir.
Yes.
Yes, sir.
So that is called a damage. That means if you are under your elastic limit, then you will find your building intact. But if the building is deformed in its non-elastic range or beyond its elastic range, then it will have some damage, which is permanent. Clear?
Yes, sir.
Now we'll come back to that definition again. So what is that? Response reduction factor depending on perceived seismic damage performance. That means here what you're allowing, you're allowing building to get damage as per your choice. Perceived means I will define seismic damage, that is a damage due to seismic activity. So I will find out that perceived seismic damage performance, and it is characterized by ductile and brittle, or brittle, not and. Either it will be ductile behavior or it will be brittle behavior. Now you can understand ductile means it is a failure. The warning of the failure is given right earlier, or there are enough in warnings that are given, and it is not sudden and it does not collapse. It gets on stretch or damaged, and finally वो crack होगा, but it will be not sudden, and if the damage is sudden then it is called brittle. तो ductile and brittle में फर्क समझ में आया?
Yes, sir.
Now what is this perceived seismic damage performance? अब ये इसकी जरूरत क्यों महसूस हुई ये मैं बताता हूं। Again, we'll go back to that graph. Now the graph is this. Now मान लो due to certain earthquake, you are having this much damage in your building. In another, uh, to 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 say that uh, this damage shall not damage the building, or this deformation shall not damage the building, you will have to analyze the structure as linear, like this. You cannot go for plastic behavior. You have to go linear, no? Clear हो रहा है ना? Hello.
Yes, sir.
Now let's say there is a severe earthquake, and due to the severe earthquake, the building is deformed up to this. Then if you want to design the building except for this damage, you have to design the building at this level. So the force, अगर इतने ज्यादा फोर्स के लिए आपको बिल्डिंग डिजाइन करना है तो क्या होना पड़ेगा? आपके क्रॉस सेक्शन बड़े हो जाएंगे, ऐसे भी बड़े हो जाएंगे, राइट? मेनी टाइम्स इट मे बी अनइकोनॉमिकल. मान लो अगर ये फोर्स के लिए आपको कॉलम डिजाइन करना है तो आपका साइज वो कॉलम का 3 मीटर बाय 3 मीटर आ रहा है, तो करेंगे आप?
No, sir.
No, sir.
और आपने किया तो कोई एक्सेप्ट करेगा?
वो भी
क्योंकि
नहीं करेगा.
वो बोलेगा यार भैया मेरे पास मेरा प्लॉट ही 15 मीटर बाय 15 मीटर है, उसमें से 3 मीटर बाय 3 मीटर का तो वो कॉलम का ही एरिया गया, तो मेरे लिए रहने के लिए लायक रह गया क्या? क्लियर है ना?
Yes, sir.
That means you cannot design even if you want, and even if your client is having lot of money, you cannot design the building for this force in elastic range. अच्छा, ये फोर्स कब आने वाला है? हो सकता है कभी वो आपको वो जो सिस्मोलॉजिस्ट है वो बोलते हैं भैया इतना डिफॉर्मेशन आपके बिल्डिंग में आ सकता है अगर वो रिश्टर स्केल 9.5 है. अब ये 9.5 रिश्टर स्केल कब आएगा? मे बी 1 in 500, और the probability of this level earthquake to hit your structure might be 1 in 500. आपको बिल्डिंग बनाना है 50 साल के लिए, आप काम कर रहे 500 साल के लिए. शाहजहां का ताजमहल थोड़ी बनाना है, वो हजारों साल रहना चाहिए. यस.
Yes, sir.
और शाहजहां को पैसे देने नहीं थे ना, उसको तो सिर्फ लोगों को पकड़ पकड़ के काम को लगाना था. आपको तो हर चीज को पैसा देना पड़ेगा. So you cannot do that. That means you have to look for the economy. और वैसे भी ये this earthquake may not visit your site. तो जो फियर है earthquake का वो कभी आया ही नहीं, या हो सकता है नेक्स्ट ईयर भी आए, because that is a probability which nobody knows. Yes. Clear?
Yes.
बट
Clear.
अगर आपका बिल्डिंग अर्थक्वेक प्रोन है तो इतना तो आ सकता है, या यू विल से दैट सर यहां तक तो हमको मालूम है कि शायद 10 साल में एक बार या 5 साल में एक बार आ सकता है. सो व्हाट यू विल डू अप टू दिस, यू विल डिजाइन योर एंटायर बिल्डिंग इन इलास्टिक जोन. बियॉन्ड दिस you will say that this is my limit. This is my limit. इससे आगे मैं जाने से मतलब you have reduced from that to this. Clear हो रहा है?
Yes, sir.
This is your response reduction. This is your response reduction. समझ में आया?
Yes, sir.
Yes, sir.
Okay. Now we'll see what our code says. Code says that for minor earthquake, your building should resist that, and it should behave elastically. That means shall not be any damage. Now ये minor earthquake हर महीने आ सकता है, 15 दिन में एक बार आ सकता है. So it is frequent, minor and frequent. Now if your building is subjected to moderate earthquake, moderate, code says that a little bit damage is accepted, and that damage I will define means non-structural elements may get damaged, but structural elements will remain intact. That means they will not get damaged. So what are structural elements? Beam, slab, column, footing, right? And what are non-structural elements? Maybe your ceiling, maybe your wall load, or BB masonry, or furnish, that is furniture that you are using, or wall hangings, etc. So there may be cracking in the windows or doors, or maybe cracking in on your plaster, ceiling plaster. It may fall down. That you can repair, and it will not take much time. And this moderate earthquake is not frequent, but it is not rare. It might visit your place once in say 5 to 10 years. तो आपका बिल्डिंग का लाइफ क्या है? 50 साल. तो 50 साल में अगर आपको एक या दो बार वो बिल्डिंग को रिपेयर करना पड़ा तो कितना खर्च आएगा? छोटा आएगा ना? यस.
Yes, sir.
Yes, sir.
Now your building may be subjected to severe earthquake. इसमें कोड से even your structure, there is a damage in your structural elements also, and the damage may be such that it may not be repairable. And after earthquake getting out, you may not be able to use that building, because ये पहले ऐसा था, earthquake आने के बाद आपका बिल्डिंग ऐसा दिखाई देने लगा. तो रहेंगे आप इस बिल्डिंग में?
No, sir.
और ऐसा इधर से फोर्स लगा के ओरिजिनल में ला सकते हैं?
No, sir.
So
No.
we will demolish it, and we will erect a new structure. And this severe earthquake might come only once, or may not come in the life span of 50 years, because this severe earthquake, occurrence of this severe earthquake is very very rare. और अगर गलती से आ भी गया हमारा नसीब, हम क्या करेंगे? Entire building will be demolished. So the building will get damaged, but collapse is prevented. See, मैंने क्या कहा? बिल्डिंग डैमेज तो हो गया मगर कोलैप्स नहीं हुआ. ओके, कोलैप्स इज प्रिवेंटेड. इट इज नॉट अलाउड टू गेट कोलैप्स्ड. तो बिल्डिंग ऐसे ही पिसा का मनोरा जैसा है. Yes.
Yes,
Yes,
sir.
sir.
So this is the basic theory for earthquake, and that's why we call the structure as earthquake resistance and not earthquake proof. So अगर आपको कोई बोलता है कि earthquake proof स्ट्रक्चर मैंने बनाया, तो समझना उसे ही कुछ मालूम नहीं, या वो समझ रहा है कि आपको कुछ समझता नहीं. Right? And that's why now again understand this perceived seismic damage. That means you have accepted the damage, but the damage is such that the building is prevented from collapse. It may not be usable later on, but the life of the people or uh, uh, a human hazard inside the building as well as nearby buildings is saved because the building does not get collapsed. Clear?
Yes,
Clear,
sir.
sir.
Now, if you apply R, then it is compulsion that you must design the building ductile. That means, see, आपने R क्यों अप्लाई किया? इकोनॉमी के लिए, मगर उसी समय आपने क्या एक्सेप्ट किया? बिल्डिंग शैल नॉट बी कोलैप्स्ड. और कोलैप्स प्रिवेंशन कब कर हो सकता है? व्हेन यू आर गोइंग फॉर डक्टाइल बिहेवियर. It may show cracking, it may show excessive deformation, but it will not get collapsed. That is the ductile behavior. So the ductile behavior, अगर आप R equal to 5 लेते हो, तो आपको डक्टाइल बिहेवियर बिल्डिंग में प्रोवाइड करना ये आपकी ड्यूटी बनती है. और अगर वो डक्टाइल बिहेवियर आपने नहीं दिया, तो whenever the building whenever the earthquake will exceed from your elastic limit deformation, the building will get collapsed. Clear? So I that ductility and R are one and same. अगर आपने एक चूज किया तो दूसरा आपको गिफ्ट में मिलेगा. क्लियर?
Yes, sir.
गिफ्ट मतलब आपको वो कंपल्शन रहेगा कि आपको डक्टाइल बिहेवियर प्रोवाइड करना है. ओके, सो नाउ अब थोड़ा आसान लग रहा है ना?
Yes, sir.
Yes, sir.
Now this essay by G, I will just only say that this is a structural dynamic concept, but it has been simplified for you by all codes of the different countries. In India, we are using it as average response acceleration coefficient, and इसके लिए हमें एक response spectra दिया है. So based on that, we'll find out essay by G. Clear? अब तक समझ में आया?
Yes, sir.
Yes.
Sir.
अब आगे चलते. अब देखो, ये बाकी तो सिंपल है. ये लोकेशन भुज का है, जोन नंबर 5 है, उसके लिए z इक्वल टू 0.36 है. कहाँ से लिया? टेबल नंबर 2 IS 1893. Being an office building, the importance factor is considered as I equal to 1. That is also from table number 6. Then building is required to be provided with moment resisting frame detail as per one. Now this moment resisting frame detail as per IS 13920. तो आपको ये पढ़ना पड़ेगा, which is talking about how to provide ductile behavior and response reduction factor that we are considering R equal to 5. You can go to table number 7, find out that and consider R equal to 5. Now this is the zone which is showing you the factors 0.10, 0.16, 24, 36. Clear? अगर वो नहीं समझता है तो IS कोड ने आपको सिटी वाइज दिया है, तो जोन फैक्टर्स फॉर सम इंपॉर्टेंट टाउन्स. अब इसमें आपका टाउन है नहीं, वो आपको देखना पड़ेगा. नहीं तो आपको ये देखना पड़ेगा. क्लियर? यस.
Yes, sir.
Clear, sir.
अब थक गए नहीं ना?
No, sir.
आगे जाएंगे कि यहाँ पे रुकेंगे? क्योंकि नाउ इट इज 9:13. हेलो. मैं इतने डिटेल में कभी नहीं लेता, बट एज यू पीपल आर इंटरेस्टेड, मैंने ये डिटेल्स में आपको समझाने की कोशिश की. आई होप दैट आई एम गिविंग यू दैट एवरीथिंग इन अ सिंपल लैंग्वेज. यस.
Yes, sir.
Yes, sir.
Yes, sir.
Definitely, sir.
तो बाद में आपको क्या करना है, कोडल प्रोविजन चेक करना है और उस पर रीड करना है. बट पहले अगर आपको नहीं समझता था तो एटलीस्ट अभी 10 to 20% मोर समझने लगेगा. ओके, तो यू कैन सी दैट
Yes, sir.
टेबल नंबर 6.
Yes, sir.
रुकेंगे क्या आगे जाएंगे? इट्स अप टू यू.
रुकेंगे.
हाँ, वही तो
Okay, sir.
मुझे, या नो प्रॉब्लम, बिकॉज सी ये थोड़ा मेरे लिए सब आसान है क्योंकि मैंने 100 टाइम्स बंद किया है, बट पहली बार ये थोड़ा ज्यादा होता है, इसीलिए आई थॉट दैट आई विल हैव अ कॉल फ्रॉम यू. नो प्रॉब्लम. सब लोग हैं या सभी लोग हैं यार अभी तक? ओके, जस्ट गिव मी योर ऑनेस्ट रिप्लाई अप टू व्हाट वी हैव सीन अप टू दिस. कंसेप्चुअली अगर आप किस चीज को नहीं समझेंगे ना, वो मैकेनिकली अप्लाई करने से कुछ समझ में नहीं आता. क्या कर रहे, क्यों कर रहे, पता नहीं. बस किताब में दिया है, सर ने बताया है और बॉस बोल रहा है इसलिए कर रहे. ऐसा ही होता है ना?
Yes, sir.
Yes. Any comment whether you understood it or liked it or you want to remaining part will go in
Yes, sir.
next. Yeah.
So, like it, sir. Especially the sir response factor.
Yes, sir.
सर ये
Response
पहले पढ़ा
reduction.
हुआ है सर ये मैंने,
हाँ.
पर जो सर रिस्पॉन्स फैक्टर आपने बताया वो कहीं मेरे को किसी ने नहीं बताया सर.
नहीं, वो एक्चुअली
उसका
वही
रियल
प्रॉब्लम.
मीनिंग सर आज मेरे को मतलब वो देख के पता चल गया कि किस वजह से वो यूज होता है.
response reduction factor. You are talking about response.
यस सर. यस.
Yes, sir.
Yeah. नहीं, मेनी टाइम सी मैंने ये आप लोगों को इसी somebody having echo with I am getting this up. Please, yeah, तो चेतन. ओके, सी मैंने इसलिए आप लोगों को ये सारी चीजें बताई क्योंकि मैंने देखा है देर आर n number of structural engineers, practicing structure engineers, बोलते नहीं यार R=3 लेंगे तो हो जाएगा. क्योंकि उन्हें रिलेशन ही पता नहीं कि आर और डक्टिलिटी का क्या संबंध है. या मेनी टाइम्स वी गो फॉर रिस्पॉन्स रिडक्शन फैक्टर इन आवर कैलकुलेशन, बट इन डिटेलिंग वो डिटेलिंग डक्टाइल डिटेलिंग प्रोवाइड नहीं करते. देन यू आर क्रिएटिंग or I will say that your structure will be subjected and it will show unpredictable behavior. क्योंकि जो आपने अभी यहाँ पे एस्यूम किया है वैसे ही उसको बिहेव करना है, तो उसके लिए जो रिक्वायरमेंट वो भी आपको प्रोवाइड करनी पड़ेगी. बराबर ना?
Yes, sir.
एनीथिंग एल्स, एनीबडी? So we'll continue with another day after tomorrow. We'll continue with this session. Actually, many times मैं एक ही सेशन में वो कवर करता हूँ, but I don't know your batch. I find it a little bit more sincere. That's why I thought that I will make it in 2 sessions. Okay.
Thank you, sir.
Yeah, thank you. Then in next session, we'll see the remaining process. Okay.
Okay, sir. Okay, sir.
Yeah. Thank you.
Thank you, sir. Good night.
Good night. Good night.
Good night.
Good
Thank
night.
you, sir.
Thanks everybody.